So we are talking about two-view geometry. So as I described briefly in the previous lecture, what this means is we are looking at two views of an image of a scene. Okay, the two views obviously taken with two cameras. Okay, so that is the situation. And what we want to see is, so there are different questions one can ask. Okay, so since the same scene point is projected through two cameras, there, I mean, obviously there might be a relation between the two image points, corresponding image points, right? So the study of this kind of, the geometry of this situation is called as two-view geometry. Okay, so we will use the following notation. So we will say that the two cameras are represented by C and C prime, which are actually the notation we were using for camera centers. Okay, so for us from now on, the camera center, so a camera can be represented either by C, which is the camera center, okay, or by P, which is the matrix of the camera. Okay, so this is the camera matrix. By the way, is the screen appearing too small? I have heard that I should put this in landscape mode. Hello?
It's fine for me now.
Okay. Or do you prefer it like this? So I will just, like the other instructors have told me that this should be like this. Is this better?
Yeah, this is better.
This is better.
Yeah. So see, so a camera can be denoted either by the camera center C or by the camera matrix P. So we could sometimes say, let C be the camera, or let the matrix P be the camera. Okay, so either of this language is fine. So right now I'm saying, so I have two cameras C and C prime, and suppose the scene point X is projected through the first camera C at a point small x, and through the second camera C at a point X prime. Okay, so we have already seen then that the first image point small x will be the camera matrix for the first camera times the scene point, right? These are equations that we saw when we studied camera matrices and homography and all that. Okay? So in single view geometry. So it is natural to expect that x and x prime should relate to each other in some way. Okay, and so that is what we want to study now. So in this context of two-view geometry, it is natural to ask some three questions. Okay, so three basic questions, and of course many particular questions as we go on. So three main questions are: one is about correspondence geometry. Okay, so correspondence geometry means exactly what we were talking about just now. Suppose you are given an image point you're given an image point, say small x in one view, and x prime in the second view. Okay, so we are considering only two views. So second view or other view is, which is not the first one. Okay, so I don't think there should be any ambiguity here. Okay, and x prime in the second view, or actually just x in the first view. Then how does this tell you about what should be the x prime in the second view? Actually, sorry. Given an image point x in the first view, how does this constrain? Which is to say, what does this tell us about the image point x prime in the second view? Okay, so the corresponding point x prime in the second view. So this is a natural question to ask. Suppose you knew in one of the images where the point is. Can you, so in the second image, instead of looking through all the points, is there a region that you can restrict to when looking for the corresponding point? Okay, so that's one natural question that arises. The second question is about the camera geometry. Okay, so not just about, so this was about image points, correspondence in the image points. The other thing you can ask is how are the camera matrices related? Okay, so given a set of corresponding points, which means matching points on the two images. Say you have a set xi corresponding with the points xi primes. Okay, for some, so you are given some number of correspondences. Okay, then what are, from this information, can you say what are the two camera matrices? What are the cameras P and P prime for the two views? Okay, finding a camera means finding this matrix which contains all the information about the camera. As we have seen in the anatomy of the camera matrix, if you have the matrix P, then you know where the camera center is with respect to the world coordinates, correct? So you know the location of the camera center, you know the focal length, you know all the internal and external parameters, right? So that means you know the camera, all right? So this is the question. If you're given this correspondence, can you find the two cameras? Okay. And the third question is more about structure, of the scene. Okay. So the third question is about scene geometry. So this is about recovering the structure of the scene from images. Okay. So this question is given, you're given a set of corresponding image points, given a set of corresponding, like before, like question 2, image points xi to xi prime. Okay. Then, and in this case, you also know the cameras. Okay. So, and the cameras P and P prime. Okay. Then what is the, so for each point, we want to find the original point in the scene. Okay. So let me just restrict to one point. So set of corresponding image points x corresponding to x prime and the cameras P and P prime. What is the scene point x that maps to x and x prime respectively in the two images? Okay, so these are three questions that can be answered. What we'll do today is talk about the first one. Okay, so given an image point x in one view, what information does this give us about the corresponding point in the second view? Okay, and is there some nice relation? Can you find one from the other? These are the kind of questions we'll talk about today. And I don't know how much of number 2 and number 3 we can cover. Okay, so this number 2, so if you are given a set of corresponding points, then from part 1 you can actually construct what is, okay, so the answer to part 1 is that yes, you can do this construction, and the construction is called the fundamental matrix. Okay, so the fundamental matrix F gives you the correspondence between x and x prime. So your x prime is f of x. Okay, so we will be able to construct this f such that x prime and x are related via this matrix. Okay, that's called the fundamental matrix of whatever setting is given to us. Okay, and the answer to the second question, then when you're given a set of corresponding points, then you have this fundamental matrix. Okay, then you can actually reconstruct these cameras from the fundamental matrix. Okay, so this process is constructing P and P prime from F. P and P prime from F. Okay, and this part is a little more complicated. So what I will try and do is cover as much as possible of 1 and 2, so that if you know these two, and if you have understood the language and understood what the fundamental matrix and all is, then this you can actually go ahead and study yourself whenever you require it. Okay, also it is possible that in one of your projects you might require, and if the need arises during the course, I will also talk about number 3. Okay, but we will focus on number 1 and 2 for now, because I also want to get finished with image formation and move on with image processing. Okay, all right, any questions so far? Anything, any comments? Okay, so if there's nothing, then so as I said, we want to address the first question right now. Okay. So this is called, the study of this 2-view geometry is called epipolar geometry. Okay, so epipolar because there are many the elements in here are called epipoles and epipolar lines and epipolar points and so on. Okay, so epipolar geometry. So the situation is as follows. Okay, so you have your so you have the camera 1 here. Okay, so always in these pictures we will have the first camera we will refer to as the camera on the left, and the camera on the right we will refer to as the second camera. Okay, just to fix a notation, nothing else. So this is our first camera on the left, second camera on the right. Okay, now so suppose you are looking at this scene point. Okay, so this point is a scene point. Okay, forget the intermediate picture for now. Okay, suppose this scene point is being viewed through camera 1. Okay, and it is also being viewed through camera 2. Okay, now so suppose this camera center, and X are the only 3 points you are looking at. Then these 3 points are going to be coplanar, right? So there is a plane which contains these 3 points. That plane is this plane pi. Okay, so consider the plane which contains these 3 points. Now, when you're viewing X through the first camera, and this is the virtual image. Okay, so the image is being placed between the camera and the object. If you remember, this is the virtual sensor or the virtual image screen, virtual image plane, I think. Yeah, so this is one thing. In this entire epipolar geometry study, we will always be working with the virtual image plane because it is convenient for understanding the geometry. Okay, okay, so the point, the line joining C and X is exactly the ray that will get projected on the point X in the image, right? So if this is the scene point, then this is the first image point. Image point in the image 1. And similarly, here you have image 2, and this is X prime, which is also image point in the second image. Okay, and the line joining X and C prime is exactly the line that projects onto this X prime. Correct? That is the image formation process. I hope this much is understandable. So the upshot is that the points C, X, capital X, X prime, and C prime are all coplanar. Okay, in fact, this entire ray and this entire ray lies on the plane. Okay, so does the line joining the camera centers C and C prime. Okay, so all these elements are important for us. All these 5 points and these three rays. Okay, all these are important for us, and all of them are coplanar. Okay, so this is the first important thing to realize. Now, what is done is, so what is our assumption? That you are given this x. Okay, you are given this image point x. Then, can you say anything about the image point x prime? That's our question. Correct. So, let me remove all this. So now there are a few more elements that we need to know. First of all, if we look at any other point on this ray, okay, so we are looking at this entire ray. Okay, for points here on this ray, any point on this ray here, all these points we know project to the same point x. Correct? All these points project to the same point x. What happens when you view these points through the other camera? So if I'm viewing this point, okay, capital X, the actual seen point through the other camera, I get small x prime. When I view another point on this ray, okay, then that is going to cut this. It is going to get projected onto this image plane at some other point, right? So that point is here. Then next, if I take this one projected through, I'll get another point. Okay, so this is a projection, right? So a straight line is going to go to a straight line segment, and all these points are going to get projected to this line segment here. Agreed? So all the points on this line joining C and, or the segment joining C and X, get projected to the segment joining. So we'll call this point some name. Okay, so the starting point of this segment is C. C gets projected to this point, this special point that C gets projected to is called as E prime. Okay. Then as you move towards X, all the points get projected onto this, this line here, or this segment here. Is this clear? Any doubts here? Okay, so if this much is clear, then we will give this some name. Okay, so this E prime is called the epipole with respect to X. Okay, so, or simply epipole. Okay, so we don't, it is clear from the situation with respect to what we are talking about. Okay, and this line segment is called the epipolar line. Epipolar line. So this one we say with respect to X, okay, or for X, because this it corresponds to this image point X. Okay, so epipolar line for X. So what is exactly the epipolar line for X? You look at all the world points that are getting projected onto X. Those world points get projected onto this line segment with respect to the other view, the second view. So that line segment is called the epipolar line for X. Okay, so what does this mean? This means that if you know this point C, this point X in the first view, okay, then to find corresponding points in the second view, you don't need to look at all the entire image. Okay, the corresponding points in the second view will be restricted to this epipolar line. Is this clear? What I just said? So what I'm saying is that if your X is given to you and you're asked where should the corresponding X prime lie in the other image, to begin with, you have so many options, right? You can look at all the points in the entire image. But what we are saying now is, since all these points that correspond to X really map only onto this line, okay, we are constrained by this. So this is the only line segment that you have to look at to find this X prime, the corresponding X prime. Okay, so if you have understood that, Well, I don't know what happened. Oops.
Hello.
Yeah.
Ma'am, so you said we will be constrained by only this line E prime X prime to look for point X prime, like X prime or X.
So if you want to see where the point corresponding to X might lie.
Huh.
Okay. So where might if you want to look for the point corresponding to X in the other image, I'm saying you don't have to look at other points in the image. It is enough to look at this segment. Okay.
Okay, ma'am.
Yeah. So now, so that is one thing. Okay. So we called this point the epipole. Now you could also reverse this situation. Okay. And so then correspondingly, this point here, okay, which is the projection of C prime when viewed from C, this is also called the epipole. Okay. So E and E prime are the two epipoles in the picture. Okay. And similarly, this segment here will be called the epipolar line for X prime. Okay. So to avoid confusion, although this symmetric nature is true, what we will always do is we will always keep our first view fixed. Okay. This is our first view and talk about the second view. Okay. Or finding elements in the second view, just to keep, the notation clean and not confused. Okay. So always we will assume that we know points or elements in the first image, and we want to find points and elements in the second image. Okay. So epipole will almost always refer to this E prime, and epipolar line for X, of course, is this segment. Okay. Yeah. This other image shows here, you can have this same thing symmetrically the other way also. Okay. All right. So this image here is showing exactly what I showed you just now. Okay. And this epipolar line, actually, although we are considering only this segment, so this segment corresponds to points between the camera center and the scene point X. Okay. But of course, this line can go on, okay, this way and this way also. Okay. So this segment also lies on this line. So you can call it the epipolar line, although we are hardly ever concerned with these points or with these points. Okay. And that line will be denoted by L prime. Okay. So that is the setting for epipolar geometry. Okay. And our notation. Okay. So there is some terminology also that I should, so whatever I talked about earlier, we will also write it down and notice a few more things about it. First, this epipole, which is what we saw here, the point of intersection of the line joining the camera centers with the image plane. Okay, so I'm not saying which image plane, any image plane. So this as well as the other E as well as E prime, both are called epipoles. Okay, this line that joins the camera centers. Okay, so this line here that joins the camera centers, that line is called the baseline. Okay, so you can also say that the epipoles or the epipole is the point where the baseline intersects the image plane, right? So that is what you can define the epipole as. You can also define the epipole as the projection of one camera center through the other. Okay, so this is the projection that you get if you are viewing C from C prime. Okay, and this epipole is what you get if you are viewing C prime through C, right? So you can so this description of the epipole is also fine. So it is the image of one camera center in the other view. We will see later that this is also this is also the vanishing point of the baseline direction. Okay, why vanishing point of the baseline direction? So this is for convenience as usual, but also to remember that the points on this are not going to get, yeah, maybe later on when we do it mathematically, I will be able to explain it better. This heuristic way of explaining is not the best. So anyway, so the epipole is also the vanishing point of the baseline direction. Okay, and we'll talk more about this later. Then what I want to talk about is the epipolar plane. Okay, epipolar plane is the plane where all this geometry is happening. Okay, so this plane pi on which all these points of interest are lying, that is called the epipolar plane. Okay, it is also the plane containing the baseline. Okay, so to make that makes the definition more general, I'll tell you why. Okay, so the epipolar plane is a plane containing the baseline. Okay, now if I make this definition, then I'm not restricted by the point X. Okay, so here, if you fix the point X, if you fix this point X, then the epipolar plane is fixed. Okay, what if you vary this point? Okay, so like in this image here, so this is X, this is the baseline. Okay, and then with respect to X, this is the plane that we are looking at. Okay, so this is a epipolar plane, passes through the baseline. But now if your X moves from here to here, okay, then your epipolar plane is this. Correct? If we define it as only the plane that passes through the baseline and don't put this restriction, then what we have is actually a family of planes. Right, your X could, the scene point could change, and so the plane can change. The only restriction is that that plane has to pass through the baseline. So you will get this family of planes like this, right? So any plane in this family of planes is an epipolar plane. Okay, so it is a one parameter family of epipolar planes. So this is a, so either we can be talking about one particular epipolar plane, or we could be talking about the pencil, depending on the context. Okay, so this is a one parameter family of epipolar planes. So one parameter family is sometimes called a pencil. Okay, so one parameter family is also called a pencil. Okay, so you will come across this word from time to time. Okay, so is it clear what epipolar plane is? If you fix this scene point X, then the epipolar plane is fixed. Otherwise, it is just this entire family of planes that passes through the baseline. Okay, then let's define the epipolar line. So the epipolar line, as we have seen, it is the intersection of the epipolar plane. Okay, so here, when we talk about the epipolar line, say this one. Okay, so what is this? This is the intersection of this epipolar plane with this image plane. Correct? So you, for talking about an epipolar line, you have to fix an epipolar plane first. Okay, so epipolar line is the intersection of the, or if of an, if you like, epipolar plane with the image plane. Okay, so again, because we have a family of epipolar planes, we will also have a family of these epipolar lines, okay, corresponding to all the different epipolar planes. Okay, so again, we will say that there is a pencil of epipolar lines. Okay, so epipolar line could be any epipolar line corresponding to a given, any epipolar plane. Okay, So anyway, it will be clear from the context what we are talking about. Are we talking about a particular one, or are we talking about the pencil? Okay. Yeah, and another important thing is that all these epipolar lines intersect at the epipole. Okay, so that is clear from the picture, but I think it is worth writing down. All epipolar lines so although we are saying line, and although we have the understanding that this is going to be the entire line, we are, when we draw, we are basically interested in this segment. So that is what is drawn. Okay, so all epipolar lines intersect at the epipole. Okay. What happens now is that when you have two image planes, okay, so this is your first image plane, and this is your second image plane. And if you fix an epipolar plane, say this one, okay, then you will get the intersection of this epipolar plane with the first plane. Okay, so that is, say, this one and this one. Okay, so any epipolar plane will intersect both the image planes and give rise to a corresponding pair of epipolar lines. Okay, so these two will be said to correspond to each other. Then you take another plane and look at the corresponding intersections. Those two will correspond to each other, and so on. Okay, so this is a point to remember, that any epipolar plane gives rise to a pair of corresponding epipolar lines. Okay. All right, so now here are some examples, okay, picture examples of trying to see what are the epipolar lines and epipolar points. Okay, so in whatever images we are seeing, actually the epipolar points will not be visible because these lines will meet at infinity, but not infinity, or somewhere outside the image. Okay, but anyway, so what you have here, okay, in B and C are two views of the same object. Okay, so if you look beyond these white lines, just forget these white lines for a moment and just look at the object, you can see that these are two views of the same urn. Okay, and we want to see which points correspond to which ones. Okay, so although, I mean, here they have only drawn it. Okay, we are not computing it here. We are only they have only drawn the epipolar lines to tell us that this epipolar line, the first one, corresponds to this one. Okay, and on the object, that means this point corresponds to this point. Okay, they have done this computation, but only drawn the picture here. So we are only looking at the pictures of these epipolar lines. This one corresponds to this one, and so on. Okay, so for actual images, this is what epipolar lines look like. Okay, and although in our geometric image these epipolar lines are meeting at the epipole, okay, in real life it can happen that you don't see the epipole. Okay, maybe these lines are going ahead somewhere and meeting. Okay, so you can imagine that these lines will meet somewhere. Okay, that will be the epipole for this image, and wherever these four lines meet, that will be the epipole for this image. Okay, so this is one example where of epipolar geometry. Here is another picture. Now in this case, what is happening is that, so here these two views were related by a rotation and a translation, which means the first camera moved with a rotation and translation to get to this second position. Okay, and so the epipolar lines actually meet. What we have here is a view where the camera has only translated. Okay, there is only a single dimensional motion, so there's only translation of the camera between these two images. Okay, so the object is fixed, the camera was at one point, and for the second image it only moved along a straight line for the second image. Okay, in this case what will happen is that, so we will of course see this when we derive the formulae. But what happens is that in this case, the epipolar lines are almost parallel. Okay, and so we say that the epipoles are at infinity. Okay, so these are two sort of examples where the epipole is not at infinity, and here the epipole is at infinity. Okay, so this happens when the motion is parallel to the image plane. All right. So now let's come back to our question of given x, how is x prime constrained? Okay, so which means given x, how can you find x prime? Just give me a moment. Okay, so in this we can see that given a pair of images, so you have two images here. Okay, then correspond to each point x in the image, there will be a point, it's not written down here, there will be a point x prime in the other image. Okay, and corresponding to this ray, there will be the epipolar line in the second image. Okay, so that epipolar line we are denoting by L prime. Okay, so to say how x prime is constrained, what we really want to say is how this x is giving rise to this L prime. Okay, or in some sense, what is the mapping between this x and this L prime? If we can find a mapping between x and L prime, then what will happen is given any other point x, you will be able to find the corresponding line here. Correct? So that is the constraint on x prime. The constraint is that x prime has to lie on that segment, on that epipolar line. Right? So the question now becomes, given x, can you construct this L prime? Okay. So yes, there is a map which will send x to L prime, and we will show that this map can be actually expressed as a projective mapping from points to lines. Okay, so points in this image plane to lines in this image plane. Okay, so what will this projective mapping do? It will take a point here and give a corresponding line here, and x prime will be a point on that corresponding line. Okay, so that map is actually called the fundamental matrix. Okay, and the fundamental matrix does a bit more. It actually gives you x prime itself. Okay, so geometrically, the idea is the following. Okay, so first what we will try and do is, given this x, we will try to construct a homography from the first image to the second image. Okay, so we know that, I mean, we have reasoned that this x, the image of x is going to lie on some line here, right? So we will try to construct a homography between these 2 points. Okay, and how are we going to locate this x prime in the first place? So geometrically, the location of x prime can be given as follows. Okay, this is the pointer. The location of x prime can be given as follows. Okay, so suppose you have nothing else. You have only this camera C and you have the camera C prime. Okay, imagine you have nothing else in this picture. What you will do is, so you have x, C. Okay, so you take the back projection of this ray, okay, and look at it in some fixed plane pi. So for this, you have to fix this plane. Okay, so this is some fixed plane. Why are we fixing this plane? Because, I mean, you could take, there are many choices for this capital X, right? So which choice do we take? For that, we fix a plane. Okay, once you have fixed a plane, then the choice of X is fixed. All right. So we start with C, take the back projection of small x to get this capital X in a fixed plane pi. Okay, then you join this ray from X to C prime. That will intersect the plane somewhere, and that will be your x prime. Okay, so this is how geometrically you can construct your x prime given only C and X. Okay, and what we will show is that this point X and this point X and this point X prime constructed in this way will be related through a homography. Okay, so homography, this is exactly what we saw last time, right? So homographies are mappings between the corresponding points in 2 images, right? If you're taking 2 images of the same object, that is exactly what this will be. This will be a homography, and since this This is called transfer. Okay, this construction that we did is called transfer. Since this transfer was done with respect to a fixed plane pi, this homography we will denote by h pi. Okay, definitely if this plane changes, then this homography will change. Okay, so that is why the homography is dependent on the pi.